In this video, we're going to learn how to find the horizontal or oblique asymptotes of a rational function. Now, there is a lot of text on the left, and feel free to pause the video and write it down ahead of time or after the video if you really want every last detail about what I'm about to go over. But each of these things I'll point out when I get to an example that deals with it. So, you'll often be given a rational function. And to find the horizontal and oblique asymptotes, we have to look at the end behavior of those functions. So the first situation that can come up is that the degree of the numerator is less than the degree of the denominator. And typically when this happens, you have a proper rational function, they call it, and the horizontal asymptote will be y equals 0. But why is that? Well, if we look at the leading term of each, for large values, for absolute value of x very large, the only thing that matters for this function would be x over 4x squared. Because when x gets big, those are the only terms that will mean anything in the numerator and the denominator. Because we're looking at end behavior with these types of asymptotes. So if we were to simplify that expression to 1 over 4x, we can say that as x approaches positive or negative infinity, y approaches 0. Because when x gets big, this just becomes 0, which means that our graph, as x gets big, just kind of flattens out at y equals 0. So we have one horizontal asymptote at y equals 0. So what does that mean for a graph? Well, we would put a horizontal line, and this just affects large values of x. So on the x-axis, this graph looks like this. It looks like it's flat against that line, then it dips down to a point and comes right back and flattens out that line again. So it looks very flat up against that line the entire time as I go far left and far right. That's what a horizontal asymptote or an oblique asymptote, which I'll get into later, does. It just tells you what happens for very large values of x. You'll notice here for the rest of these examples, like I drew in what the vertical asymptotes to be roughly around, so we can really focus in on what the horizontal asymptote does to the graph. So for the next example we're going to look at r of x is equal to 8x squared minus x plus 2 over 4x squared minus 1. Now for any other situation where the degree of the numerator is greater than or equal to the degree of the denominator, we use long division to find out what the end behavior would be. So I'm going to divide these two polynomials using long division. So 4x squared, I'm going to put a plus 0x to put up a little placeholder in there. Minus 1 goes into 8x squared minus x plus 2. Now I ask myself, how many times does 4x squared go into 8x squared? That's twice. So I'll put a 2 up here. And then 2 times 4x squared is 8x squared. 2 times 0 is 0. And 2 times negative 1 is negative 1. Then I'll subtract. So that's 0. Then negative x minus 0 is negative x. And then 2 minus negative 2 is plus 4. So the quotient when we're done with this is 2 plus the remainder, negative x plus 4, over the divisor, 4x squared minus 1, which we talked about earlier. This just goes to 0 because the numerator in the top is lower than the one on the bottom. But the rest of the function approaches y is equal to 2. So that quotient that you end up with is your horizontal asymptote. At y equals 2. So on my graph, I would put a horizontal line at the y value of 2. And the way that would affect the graph is that the graph, as I approach negative infinity and positive infinity, flattens out against that line, but it still has to obey the other asymptotes in place. So you'll see here that it will still approach those vertical asymptotes in a very similar way as you've seen it before. But when I go to flatten out for large values of x, it'll flatten out on that line. Now, you may see these lines touch the horizontal asymptotes, and that's okay. It won't touch it once you have a large value of x. It'll kind of just follow it forever. But in between, like this could have touched that line and it'd be safe. It's safe to draw it that way. But you'll see here they flatten out along that line. So here now we see that the degree in the numerator is actually bigger than the denominator. So when they're equal to each other, you'll notice that the horizontal asymptote is just the coefficients in front of those terms. Like 8 over 4 is 2. So the horizontal asymptote is 2. But now whenever it's more, we have to go through our long division, and this could lead to an oblique asymptote or no horizontal or oblique asymptote. So here we have the numerator is bigger than the denominator, so I'm going to use long division again. Again, I'm going to put placeholders in certain spots. So I'll have x to the third minus x squared plus 0x plus 1 dividing into 3x to the fourth plus 0x cubed minus x squared plus 0x plus 0. How many times does x cubed go into 3x to the fourth? Well, 3x times. So 3x times x cubed is 3x to the fourth. 3x times negative x squared is negative 3x cubed. 3x times 0 is 0. And 3x times 1 is 3x. Then we subtract. This is called polynomial long division, by the way. 3x to the fourth minus 3x to the fourth is 0. 0 minus negative 3x cubed is positive 3x cubed. Negative x squared minus 0 is 0. And 0 minus 3x is negative 3x. And then we'll carry down that 0 and do the same process. How many times does x cubed go into 3x cubed? A positive 3 times. So 3 times 3x cubed is 3x cubed. 3 times negative x squared is negative 3x squared. 3 times 0 is 0, and 3 times 1 is 3. Then you subtract. So 3x cubed minus 3x cubed is 0. 0 minus negative 3x squared is positive 3x squared. Negative 3x minus 0 is negative 3x. And 0 minus 3 is negative 3. So we end up with, when we divide these two polynomials, is 3x plus 3 plus your remainder, 3x squared minus 3x minus 3 over x cubed minus x squared plus 1, which again, since the numerator's degree is less than the denominator, that all goes towards 0. But what's left is how the function behaves. Now this is a line, so it's just not horizontal like you saw with 0 and with 2. So we call this an oblique asymptote. Whenever it represents a line of the form ax plus b or mx plus b, that is referred to as an oblique asymptote. So if I were to draw that out, I would have a line at like y is equal to 3, a slope of 3. When I draw this graph out, it'll look something like this, where it'll follow that line towards negative infinity, still obey the other asymptotes. You'll see here that this graph actually crosses across the oblique asymptote, and then we'll continue to follow along that horizontal line. So you'll see here how it affects. As for large values of x, it'll just keep following that line, but in the middle, it'll obey these vertical asymptotes more. And that's called an oblique asymptote. So whenever the difference between the 2 degrees is 1, that leads to a line referred to as an oblique asymptote. Now anything usually bigger difference than 1 There is no horizontal or oblique asymptote, but let's talk about what the division tells us about the graph and how it affects it. So here we can already tell, since the numerator has a degree 2 more than the denominator, there shouldn't be a horizontal or oblique asymptote. So there is no asymptote here. But let's show what that division actually tells us. So we're going to divide 2x to the 5th minus x cubed plus 2 by x cubed minus 1. So x cubed plus 0x squared plus 0x, put little placeholders in, minus 1 is going to divide into 2x to the 5th plus 0x to the 4th minus x cubed plus 0x, plus 0x squared plus 0x plus 2. And I ask myself, how many times does x cubed go into 2x to the 5th? That would be 2x squared times, so 2x squared times x cubed is 2x to the 5th. 2x squared times 0 is 0. 2x squared times another 0 is another 0. And then 2x squared times negative 1 is negative 2x squared. And I'll subtract that away. 0, 0. Negative x cubed minus 0 is negative x cubed. 0 minus negative 2x squared is positive 2x squared. Then we'll carry down the other two terms, 0 and 2. And we'll ask ourselves the same question. How many times does x cubed go into negative x cubed? Negative 1 times. So negative 1 times x cubed is negative x cubed. Negative 1 times 0 is 0. Negative 1 times another 0 is 0. And negative 1 times negative 1 is a positive 1. And then we'll subtract that away. So 0, 2 minus 0 is 2x squared. 0 minus 0 is 0. And then 2 minus 1 is positive 1. So when I divide these two, I get 2x squared minus 1 plus the remainder, 2x squared plus 1, over the divisor x cubed minus 1. Again, the remainder there follows the same rules as that first example. That'll just go to 0. But the rest of the graph behaves like this function, which means that there is no horizontal or oblique asymptote, because that's a quadratic function, not a line. But what happens with the graph is that is a quadratic with a y-intercept at negative 1. And then you'll see here that it will make a parabola. And the way the graph behaves is it will follow that parabola like normal for large values of x goes to the far left. You'll see here it kind of breaks away. Then it'll follow that vertical asymptote. And then it'll come back down and again follow that quadratic again. So if I were to really zoom out in this graph, you'll see a very prominent parabola with a slight bend in the middle of it. And so that's what all this is breaking down. So just to go over, if it's a proper rational function, meaning the degree of the numerator is less than the degree of the denominator, horizontal asymptote is y equals 0. You don't have to go through this process. You just say it's 0. Now, whenever those degrees are equal to each other, or greater than, we use long division to see what it is. It's usually the quotient of what you have left after you divide. But if they're equal, the horizontal asymptote will be the leading coefficients over each other. So in this case, 8 over 4 gave us 2. That would be the horizontal asymptote. But if you see the difference between the degrees is 1, that's an oblique asymptote, which is usually represented by a line that you can only get whenever you use long division here. And if it's anything bigger than 1, like 2 or 3 or 4, there is no oblique or horizontal asymptote. The function just behaves like the function you get after long division, and it follows it for large values of x. And that is how you find the horizontal and oblique asymptote of a rational function.